What if you could step outside of time itself, where a single hour near the edge of a black hole could stretch into 100 years back on Earth? This isn't science fiction. It's the mind-bending reality of time dilation, one of the universe's most astonishing phenomena. Picture a cosmic time machine warping the very fabric of reality, where gravity's grip is so strong that time itself slows to a crawl. Black holes don't just swallow light, they twist time into something unrecognizable, turning seconds into centuries and moments into millennia. And today, we're diving headfirst into this gravitational mystery, unraveling how these cosmic monsters rewrite the rules of existence. Think about the sheer power it takes to bend time. Here on Earth, our lives tick by at a steady rhythm, but near a black hole, gravity becomes a sculptor, molding time like putty. Imagine standing on the edge of one, your feet anchored in a place where every heartbeat stretches into an eternity, while the rest of the universe races forward without you. It's a paradox that defies intuition, yet it's etched into the laws of physics. Einstein's theory of relativity predicted this over a century ago, but even now, the implications leave us breathless. What would it mean for exploration, for survival, or even for love if time itself became fluid? This is the allure of black holes, not just as destroyers, but as portals to understanding the universe's deepest secrets. They challenge everything we think we know about reality, offering glimpses into a world where time is no longer a constant but a variable. And as we explore this phenomenon together, you'll discover how these gravitational giants could redefine the future of space travel, aging, and even the fate of civilizations. So buckle up, we're about to journey into the heart of one of space's greatest enigmas, where the clock doesn't just tick, it warps. To understand how black holes bend time, let's start with Einstein's revolutionary idea: time isn't fixed. It's more like a river flowing at different speeds depending on where you are. His theory of relativity showed that gravity doesn't just pull objects, it stretches time itself. Picture two identical clocks, one placed on Earth's surface, the other launched into space. Over years, the space clock ticks slightly faster because Earth's gravity tugs weaker on it. The difference is tiny, mere microseconds over decades, but it proves time isn't absolute. It bends under gravity's weight. Now amplify that effect to extremes. A black hole's gravity isn't just strong, it's catastrophic, warping spacetime so severely that time nearly grinds to a halt near its edge. Imagine a daring astronaut skimming close to the event horizon. To them, minutes might pass normally, but back on Earth, centuries could fly by. This isn't a glitch in reality, it's the universe obeying its own rules. The closer you get to infinite gravity, the more time distorts, like a record player slowing a song to a drugged crawl. Think of spacetime as a trampoline. Earth's mass creates a gentle dip, barely bending the fabric, but a black hole, it's a bottomless pit, twisting the trampoline so sharply that time itself stretches thin. That's why near these cosmic monsters, the universe's clockwork unravels. Seconds stretch into years, and a single orbit could outlast civilizations. It's a place where physics as we know it surrenders to the bizarre, and that's what makes black holes the ultimate time machines. A black hole isn't just a cosmic vacuum cleaner, it's the universe's most extreme gravity well, a place where matter gets crushed into oblivion. To grasp how these monsters form, picture a dying star, one far more massive than our Sun. When such a star burns through its fuel, the outward pressure of nuclear fusion can no longer fight the inward pull of gravity. The star collapses in on itself, imploding with such force that even atoms are smashed. What's left is an infinitely dense point called a singularity, surrounded by an invisible boundary known as the event horizon, the point of no return. Step beyond it, and not even light can escape. Think of spacetime as that trampoline again. Place a marble on it, and the fabric barely bends. Now drop a bowling ball. The indentation is deep, steep, almost bottomless. That's a black hole's grip on the universe. Its gravity is so intense that it warps everything around it, bending light, stretching time, and swallowing anything that strays too close. Even sound can't exist here. The silence is absolute, broken only by the invisible scream of space-time itself being torn apart. But here's what's even wilder. Black holes come in different sizes. Some are just a few times heavier than our Sun, while supermassive ones like the one at the center of our galaxy weigh as much as millions or even billions of suns combined. And yet, no matter their size, their power to distort reality is the same. Imagine a whirlpool in space spinning faster and faster, dragging everything into its vortex. That's the irresistible pull of a black hole's gravity, a force so relentless it rewrites the rules of physics. What makes them truly terrifying, though, isn't just their hunger. It's their ability to stretch and squeeze anything that falls in a process scientists call spaghettification. Picture an astronaut approaching the event horizon feet first. The gravity at their feet is so much stronger than at their head that their body gets pulled like taffy, stretched into a thin, noodle-like strand. Even atoms aren't spared, they're ripped apart, their particles scattered into the void. It's a fate worse than any sci-fi horror, a real-life cosmic shredder. Yet, for all their destructive power, black holes are also creators. The energy they release can ignite new stars, shape galaxies, and even seed the universe with the building blocks of life. They're not just destroyers, they're catalysts, sculpting the cosmos in ways we're only beginning to understand. And that's the paradox of black holes. They're both the end and the beginning, the darkest pits in space and the engines of creation. The event horizon isn't just a boundary, it's the ultimate cosmic deadline. Cross it and there's no turning back, no second chances, not even a desperate SOS signal. This invisible line marks the point where a black hole's gravity becomes so overwhelming that escape velocity exceeds the speed of light. And since nothing in the universe can outrun light, nothing, not particles, not spacecraft, not even information itself, can ever return. But here's where it gets even stranger. The event horizon isn't just a physical barrier. It's a time warp of unimaginable proportions. Picture an astronaut drifting toward a black hole. As they inch closer to the event horizon, time for them would appear to pass normally. But to someone watching from a safe distance, the astronaut's movements would slow down, their signals stretching into longer and longer wavelengths until they seem to freeze in place. The distant observer would never actually see them cross the horizon. Instead, the astronaut would fade into darkness, their image redshifted into oblivion as if time itself had pressed pause. This eerie illusion isn't a trick of perspective, it's the universe bending under extreme gravity, warping reality until time and space trade places. Think of it like walking toward a waterfall's edge. From far away, you see the water plunge over the brink, vanishing instantly. But if you were floating in the current just before the drop, your experience would be different. The water around you moving smoothly, unaware of the looming precipice. The event horizon works the same way. To the doomed astronaut, crossing it might feel uneventful, even imperceptible. Yet from the outside, their final moments stretch into eternity. This paradox reveals something profound about black holes. They don't just trap matter, they trap time. The closer you get to the event horizon, the more time dilates, slowing to an infinite crawl at the boundary itself. It's as if the universe slams on the brakes, stretching seconds into eons for those watching from afar. And once you cross, time's arrow inside the black hole no longer points forward. It spirals inward toward the singularity, where physics as we know it ceases to exist. What does this mean for our understanding of reality? For one, it shatters the illusion of a universal clock. Time isn't a steady metronome ticking the same for everyone. It's a fluid, malleable thing bent by gravity's will. The event horizon is the ultimate proof, a place where time fractures, where now for one observer is forever for another. It's a reminder that the universe operates by rules far stranger than fiction, where even the simplest concepts, like the passage of time, can unravel into the extraordinary. Let's make this cosmic phenomenon personal. Imagine two identical twins. One stays safely on Earth, while the other embarks on a mission orbiting near a black hole's event horizon. For the daring twin, time flows normally. Their heartbeat, their breath, their thoughts all unfold at the same steady pace they've always known. But when they return to Earth after what feels like a few hours, they'd step into a world where decades or even centuries have passed. The sibling they left behind is now an elderly stranger, and the civilization they knew might be unrecognizable. This isn't just a sci-fi plot, it's the brutal reality of time dilation in extreme gravity. Why does this happen? Think of gravity as a cosmic anchor dragging on the very fabric of time. Near a black hole, that anchor is so heavy it stretches seconds like taffy. The twin near the event horizon isn't moving slower. Their time itself is warped like a clock submerged in molasses. Meanwhile, the Earth-bound twin's timeline rushes forward unimpeded, like a river flowing at normal speed beside a stagnant pond. The difference isn't an illusion, it's the universe enforcing its rules with ruthless precision. Here's another way to visualize it. Suppose both twins could send light signals to each other every second. For the one near the black hole, those signals leave at regular intervals, but by the time they reach Earth, they'd be stretched out, arriving minutes or even years apart. The distant twin would see their sibling frozen in slow motion, their movements drawn out, their signals creeping in like whispers across an ever-widening chasm. It's as if the black hole's gravity is stretching the very threads of time, making each second for the astronaut count for years elsewhere. Now push this thought experiment further. What if the adventurous twin hovered just outside the event horizon where time dilation becomes infinite? From Earth's perspective, their approach would appear to slow to a standstill. They'd never quite cross the horizon, frozen in time like a photograph, their fate suspended in the eyes of distant observers. Yet for the twin in the black hole's grip, time marches forward relentlessly. In moments, they'd be pulled past the point of no return, vanishing from the universe's timeline altogether. This paradox reveals something profound. Time isn't just relative, it's deeply personal. Two people can experience the same event in radically different ways, separated not by distance, but by the warping of space-time itself. It's a reminder that the universe doesn't care about our intuition. It operates on rules that defy everyday experience, where gravity can bend time until the familiar becomes alien. And that's what makes black holes the ultimate laboratories for understanding reality's deepest mysteries. The satellites orbiting Earth right now, those unassuming machines guiding your GPS, are proof that time dilation isn't just theoretical. Every day they correct for a tiny but crucial time warp. Because they're farther from Earth's gravity, their clocks tick about 45 microseconds faster each day than ours on the ground. Without accounting for this, your navigation would drift off by nearly 10 kilometers daily. It's a subtle reminder, even Earth's gentle gravity bends time. But swap our planet for a black hole, and those microseconds explode into lifetimes. Take the same principle and crank it to cosmic extremes. Near a black hole, gravity doesn't nudge time, it hijacks it. Where satellites gain microseconds, an astronaut near the event horizon could lose years. Imagine a spaceship hovering just outside the point of no return. For every minute the crew experiences, decades might pass on Earth. A coffee break for them could mean their home planet advances into a new era. The contrast couldn't be starker. Earth's time warps are like ripples in a pond, while a black holes are tidal waves swallowing the shore. Here's another way to frame it. Think of time as a rubber band. On Earth, gravity stretches it slightly, enough to matter for precision tech, but barely noticeable otherwise. Near a black hole, that rubber band snaps. Time stretches so thin that moments fracture into eons. A single orbit around a black hole could outlast human civilization, with the universe outside racing ahead like a movie on fast forward. It's the difference between a gentle breeze bending a blade of grass and a hurricane uprooting entire forests. Yet these extremes share a common thread: they obey Einstein's rules. Whether it's satellites or black holes, gravity's grip on time is predictable, measurable, and utterly indifferent to human scales. That's the brilliance of relativity. It works just as well for your GPS as it does for a collapsing star. The universe doesn't care if the effect is microseconds or millennia. It plays by the same equations either way, and that's what makes black holes so thrilling. They're not exceptions to the rules, they're the rules written in fire, showing us what happens when gravity truly runs wild. So the next time your phone guides you home, remember, those satellites are dancing on the edge of a time warp. And out there, in the darkness, black holes are doing the same dance with reality itself as their partner. The Schwarzschild radius isn't just a measurement, it's the point of no return, the exact distance where a black hole's gravity becomes so overpowering that even time itself surrenders. Named after physicist Carl Schwarzschild, who solved Einstein's equations for a non-rotating black hole, this invisible boundary defines the event horizon. But here's what's staggering. At this precise radius, time dilation doesn't just slow down, it effectively stops for anyone watching from afar. A clock falling toward the black hole would appear to freeze at the Schwarzschild radius, its ticking stretching into infinite silence. Why does this happen? Picture a beam of light trying to escape the event horizon. Gravity here is so intense that the light's wavelength gets stretched to infinity, redshifted into nothingness. For an outside observer, this means any signal, a clock's tick, a heartbeat, even the glow of a spaceship's engine would smear into eternity. The closer an object gets to the Schwarzschild radius, the longer its light takes to reach us, until time between signals stretches to infinity. It's like watching a movie where the frames slow until the screen goes dark, but the film never actually ends. Now, think about what this means for the doomed object crossing the horizon. From its perspective, time flows normally. There's no sudden stop, no cosmic pause button. The disparity between these two viewpoints, the infinite freeze witnessed from outside versus the uneventful passage felt inside, reveals one of relativity's most unsettling truths: time isn't universal. It fractures under extreme gravity, splitting reality into two irreconcilable experiences. This paradox has a name: gravitational time dilation. Near the Schwarzschild radius, the gravitational pull warps spacetime so severely that time's flow bends to a halt relative to distant observers. It's as if the black hole's gravity digs a pit so deep that time can't climb out. The equations are clear: time dilation becomes infinite at this threshold. But infinite doesn't mean time ceases to exist. It means the universe's ledger breaks down. For those watching from safety, the falling object becomes a fossil, eternally suspended at the edge of oblivion. Here's where it gets even stranger. The Schwarzschild radius isn't just a barrier, it's a one-way mirror. From outside, nothing ever seems to cross it, frozen in a ghostly tableau. But from inside, the boundary passes unnoticed. There's no wall, no alarm, just the inexorable pull toward the singularity. This duality underscores the raw power of general relativity. Reality isn't just stranger than we imagine, it's stranger than we can imagine, a place where the laws of physics twist time into knots even as they hold the cosmos together. So what's the takeaway? The Schwarzschild radius isn't just a line in the sand. It's the universe's ultimate hourglass, where time's sand grinds to a halt for observers while pouring relentlessly for those brave or doomed enough to cross it. It's a reminder that black holes don't just bend space, they shatter our most fundamental notions of time, leaving us with a chilling question. If time can stop at the edge of a black hole, what else about reality might we have wrong? Spaghettification isn't just a gruesome fate, it's a cosmic tug of war where gravity plays by its own twisted rules. Picture an astronaut drifting toward a black hole. As they near the event horizon, the pull on their feet becomes infinitely stronger than on their head. The result, their body stretches like hot cheese, atom by atom, into a noodle-thin strand. But here's the twist: while tidal forces are shredding them apart, time dilation is playing tricks too. To an outside observer, the astronaut's gruesome transformation would appear to slow to a crawl, freezing mid-stretch like a bug in amber. It's a macabre ballet of physics where space rips you apart and time stretches your agony into eternity. Think of it like taffy in zero gravity. Pull on both ends and it thins out in the middle, but now imagine one hand pulling harder than the other. That's spaghettification in action, an uneven gravitational grip that elongates anything unlucky enough to wander too close. Yet at the same time, the black hole's time warping effect means the taffy would appear to stretch slower and slower to someone watching from afar. The closer it gets to oblivion, the more it seems to freeze, even as it's being torn to pieces. It's a paradox that defies intuition: destruction and stasis happening simultaneously, depending on who's looking. Now add another layer to this nightmare. While the astronaut's body is being spaghettified, their own experience would be bizarrely different. Thanks to time dilation, their final moments, stretched thin like their limbs, might feel like an eternity to them, even as they vanish from the universe's timeline in an instant. Imagine being both shredded and suspended, your last second stretched into subjective eons, your atoms unraveling like a cosmic thread. It's a fate worse than any horror movie where physics itself becomes the villain. But here's the wildest part: this isn't just theoretical. Scientists have observed stars being spaghettified by supermassive black holes, their light flaring as they're torn apart in events called tidal disruption events. These cosmic snacks leave behind glowing signatures, a last scream of light redshifted and stretched by the very forces destroying them. And just like our doomed astronaut, these stars appear to freeze at the event horizon from our perspective, their final moments smeared across time like a distant echo. So what's the takeaway? Black holes don't just bend the rules, they rewrite them with violent flair. Spaghettification and time dilation aren't separate phenomena. They're two sides of the same nightmare where gravity's grip distorts both space and time into something unrecognizable. It's a reminder that the universe isn't just stranger than we imagine, it's stranger than we can imagine, a place where the fabric of reality frays at the edges, and the laws of physics become a funhouse mirror of their usual selves. Black holes aren't just cosmic vacuum cleaners, they're also slow, silent evaporators, thanks to a bizarre quantum quirk called Hawking radiation. Picture the event horizon as a stormy sea, where pairs of virtual particles constantly flicker in and out of existence. Normally, these particles annihilate each other almost instantly. But near a black hole's edge, gravity's grip is so extreme that one particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over unimaginable timescales, this drip feed of lost energy causes the black hole to shrink. And here's where time dilation throws in a cosmic curveball. The escaping particles carry away mass, but from an outside observer's perspective, this evaporation happens in ultra-slow motion. Why? Because time near the horizon is stretched to near infinity. A black hole that might take billions of years to evaporate from its own frame of reference could appear to linger for trillions of years to someone watching from afar. It's like watching a candle burn underwater. The flame still consumes the wax, but everything slows to a glacial pace. Now, pair this with the mind-bending fact that smaller black holes evaporate faster. A tiny black hole might vanish in a burst of radiation over centuries, while a supermassive one could outlast the universe itself. But here's the twist: as the black hole shrinks, its Hawking radiation intensifies, accelerating its own demise. Imagine a block of ice melting, first slowly, then faster as it becomes smaller and hotter. The final moments, a spectacular pop of energy, a last gasp of particles freed from gravity's clutches. What's truly wild is that this process ties quantum mechanics directly to relativity. Virtual particles, a quantum phenomenon, are shaped by the black hole's warped spacetime. The particles that escape do so because time dilation near the horizon stretches their window of opportunity, allowing one to flee while the other is doomed. It's a dance between the universe's smallest rules and its most extreme forces, proof that even in the darkest corners of space, quantum weirdness leaves its mark. So while black holes might seem eternal, they're on a cosmic clock ticking toward their end, one particle at a time. And thanks to time dilation, that clock runs at a different speed for everyone watching, a reminder that in the universe's grand scheme, even oblivion is relative. Christopher Nolan's Interstellar gave us one of the most visually stunning depictions of a black hole ever put on screen. Gargantua, a supermassive beast with an accretion disk glowing like a cosmic halo. But beyond the spectacle, the film's portrayal of time dilation, especially on Miller's waterlogged planet, is where science and cinema collide in fascinating ways. The movie nails a key truth: the closer you orbit a black hole, the more time slows catastrophically. 1 hour on Miller's planet equals 7 years back on Earth, a mind-bending effect rooted squarely in real physics. That relentless tidal wave chasing Cooper's crew, artistic license, sure, but the time warp they're racing against, that's Einstein approved. What makes Interstellar's science stand out is its collaboration with astrophysicist Kip Thorne, who ensured Gargantua's gravitational lensing and time dilation adhered to relativity's equations. The rendering of the black hole itself, a swirling vortex of bent light, was so accurate it led to genuine scientific papers. But here's where fiction flexes its muscles. Miller's planet orbits so close to Gargantua that the tidal forces would likely shred it, not just flood it. And those waves towering like skyscrapers, they'd require impossibly shallow water or a gravity gradient so extreme it'd pancake anything trying to land. The film trades pure realism for visceral stakes, compressing years of grief into a desperate hour, making time dilation feel urgent, not just theoretical. Then there's the emotional core, Cooper watching his children age decades in minutes. That gut punch works because the science behind it is sound. Time doesn't just slow near a black hole, it fractures relationships, stretching moments into lifetimes. The movie's genius is turning equations into agony, letting us experience relativity's cold math through a father's helplessness. But real-life time dilation near a black hole would be even more extreme. On Miller's planet, seconds drag like molasses. Near the event horizon, time would practically stop for outside observers. Nolan's compromise, a planet far enough to be survivable but close enough to twist the knife. The balance Interstellar strikes is rare, honoring the science while bending it for story. Gargantua's portrayal is a masterpiece of accuracy, but Miller's planet is a pressure cooker, amplifying time dilation's emotional weight beyond what physics strictly allows. It's a reminder that sometimes the truth needs a little fiction to hit us where it hurts, and that's okay. The movie's legacy isn't just in its spectacle, but in making audiences feel the raw, terrifying wonder of a universe where time isn't fixed, where gravity doesn't just bend light but bends lives. When two black holes spiral toward each other in a deadly dance, they don't just collide, they send shockwaves through the fabric of spacetime itself. These gravitational waves, first detected in 2015, are more than ripples in a cosmic pond. They're the direct result of time and space being stretched and squeezed as the black holes merge, warping reality in ways that echo across the universe. But here's the twist: the closer these titans get to merging, the more extreme their gravitational pull becomes, bending time itself like taffy in the moments before collision. Picture this: two black holes, each billions of times heavier than our sun, orbiting each other at nearly light speed. As they tighten their spiral, their immense gravity distorts spacetime so severely that time for them slows to a crawl compared to the rest of the universe. A single second near the merging black holes could stretch into hours or even years for distant observers. It's as if the universe hits pause on their local timeline while the cosmic clock everywhere else keeps ticking. This time dilation isn't just a side effect, it's written into the gravitational waves they emit, encoded in the very signals we detect here on Earth. Now consider what happens during the final plunge. In the last milliseconds before merger, the black holes orbit so fast that time near them practically freezes from our perspective. The gravitational waves they produce carry this extreme time warp, stretched into lower frequencies as they travel across the cosmos. By the time these waves reach us, they've weakened, but their structure still holds clues about the violent time distortions that created them. It's like listening to a recording of a scream slowed down to a deep, rumbling groan. The original event was a split-second cataclysm, but the echoes we hear are drawn out, a relic of time bending under unimaginable strain. What's even wilder is how these mergers reveal the universe's flexibility. When black holes collide, they don't just warp space, they warp our understanding of time's flow. The gravitational waves they produce are proof that space-time isn't a static stage but a dynamic, elastic fabric that can twist, vibrate, and even ring like a bell. And just as a bell's tone depends on its shape and size, the sound of a black hole merger, those chirps and rumbles picked up by detectors like LIGO tell us about the masses involved, their spins, and how time itself behaved in their final, frenzied moments. Think of it like throwing a pebble into a pond. The ripples spread outward, carrying information about the splash, the pebble's size, the force of the throw. Gravitational waves do the same, but instead of water, they ripple through space-time, encoding the black hole's time-distorted death spiral. And just as ripples can interfere with each other, creating complex patterns, the gravitational waves from merging black holes bear the fingerprints of time dilation, subtle shifts in frequency that reveal how gravity's grip twisted time itself during the event. This isn't just theoretical. The black hole merger observed in 2015, dubbed GW 150914, showed exactly this. The signal's rising pitch and amplitude matched predictions of how time dilation would stretch the waves as the black holes neared collision. It was as if we'd tuned into the universe's own slow-motion replay, watching time bend in real time. Future detections will only sharpen this picture, revealing how time warps under even more extreme conditions, like when supermassive black holes, millions of times heavier, eventually merge in the hearts of galaxies. So what does this mean for our understanding of reality? Black hole mergers aren't just cosmic spectacles, they're natural laboratories for testing relativity's wildest predictions. By studying their gravitational waves, we're not just listening to the universe's soundtrack, we're decoding how time itself behaves under forces so intense they defy imagination. And with every new detection, we get closer to answering one of physics' biggest questions. In a universe where time can stretch, freeze, and shatter, what other secrets is gravity hiding? If black holes are the universe's relentless vacuum cleaners, sucking in everything without mercy, then white holes are their bizarre theoretical opposites, cosmic fire hydrants blasting matter and energy outward without end. These hypothetical beasts, predicted by the same equations that describe black holes, are like rewinding a cosmic film. Where a black hole's event horizon is a one-way door inward, a white hole's is a one-way door outward. Nothing enters, only exits, and here's where the mind-bending question kicks in. If black holes slow time to a crawl, could white holes reverse it entirely? Picture a singularity exploding instead of collapsing, a big bang in miniature, vomiting space-time like a cosmic geyser. According to general relativity, white holes are mathematically possible, but they'd violate the second law of thermodynamics by magically decreasing entropy, essentially unscrambling the universe's disorder. That's why most physicists treat them as mathematical curiosities rather than real objects, but let's indulge the fantasy. If time near a black hole stretches toward infinity, could a white hole's extreme repulsive gravity flip the script, making time flow backward? The equations hint at eerie symmetries. While black holes trap light, white holes repel it. Where black holes stretch matter into spaghetti, white holes might spit it out fully formed. Imagine watching a white hole from afar. A burst of energy erupts, perhaps remnants of a long-dead star, or even an entire universe compressed into a singularity. But from the white hole's perspective, time might be running in reverse. A clock near its boundary could tick backward relative to ours, as if the universe itself hit rewind. This isn't just sci-fi. Some interpretations of quantum gravity suggest white holes could be the other end of black holes, connected by an Einstein-Rosen bridge, yes, a wormhole. In this wild scenario, what falls into a black hole might emerge from a white hole elsewhere, or elsewhere with time flowing in the opposite direction. Here's the catch: white holes are catastrophically unstable. Unlike black holes, which thrive on their own gravity, a white hole's outward explosion would instantly collapse under any external matter trying to enter, likely triggering a new black hole. They're like cosmic soap bubbles, beautiful in theory, but popping the moment reality pokes them. Still, their theoretical existence forces us to ask profound questions. Is time's arrow truly irreversible, or could extreme physics flip it? If we ever detected a white hole's signature, a sudden, unexplained burst of energy with no precursor, it would upend our understanding of causality itself. For now, white holes remain ghosts in the equations, shadows of what the universe might permit under conditions we've yet to witness. But their allure isn't just in their defiance of physics, it's in their reminder that the cosmos is far stranger than our intuition allows. Black holes warp time, white holes might twist it backward, and in that tension between attraction and repulsion, between past and future, lies the unsettling possibility that time itself is more fluid than we dare believe. Wormholes aren't just science fiction, they're theoretical tunnels through space-time, potentially linking black holes to white holes or even distant corners of the universe. But here's the twist: if black holes warp time to a crawl, could a traversable wormhole turn that dilation into a time machine? The math suggests it's possible, under conditions so extreme they border on fantasy. Picture a shortcut between 2 points in spacetime, where one mouth of the wormhole sits near a black hole's crushing gravity, and the other rests in calm, flat space. Time would pass slower near the black hole's mouth, meaning if you hopped in, you might emerge years, or even centuries before you left. It's relativity's ultimate loophole, where time dilation isn't just an effect but a tool. Einstein's equations allow for these bridges, known as Einstein-Rosen bridges, but with a catch: they'd snap shut instantly unless propped open by something with negative energy, a hypothetical substance that defies gravity's pull. Think of it like trying to hold open a collapsing tunnel with anti-gravity ropes. Even then, the radiation and tidal forces near a black hole's mouth would likely shred anything attempting the trip. But let's suspend disbelief for a moment. If you could stabilize a wormhole, the time difference between its ends would create a natural time machine. Step in on Monday, exit on the previous Friday. It's a paradox wrapped in a singularity where causality itself starts to unravel. Theoretical models take this even further. Imagine moving one wormhole mouth at near light speed while keeping the other stationary. Time dilation would stretch the traveling mouth's timeline, creating a mismatch between the two ends. Return the moving mouth to its origin, and you'd have a closed loop where entering the wormhole could send you back to the moment it was created. It's like folding a piece of paper so sharply that 2 points in time touch. The implications are dizzying, messaging your past self, preventing disasters, or trapping history in infinite loops. But here's the rub: quantum mechanics likely forbids it. The universe seems to have a built-in no free lunch policy for time travel, with paradoxes like killing your own grandfather triggering self-correcting mechanisms that would collapse the wormhole before mischief occurs. Still, the idea isn't entirely dead. Some physicists speculate that microscopic wormholes could exist, threaded by cosmic strings or stabilized by exotic matter. These wouldn't fit a person, but they might allow information to traverse time, hinting at a universe where the past and future are subtly intertwined. Others suggest that wormholes could explain quantum entanglements, spooky action at a distance, with particles linked through hidden space-time tunnels. It's a stretch, but it underscores how deeply time and space might be connected. So where does that leave us? Wormholes dangle the tantalizing possibility of bending time to our will, but reality keeps slamming the door. They're mathematically possible, physically improbable, and cosmically unfair, teasing us with shortcuts we can't take. Yet even as theory clashes with nature's limits, wormholes remind us that the universe's rulebook is stranger than we dreamed. Black holes warp time, wormholes might knit it, and in that tension between impossibility and imagination, physics keeps its most thrilling secrets. At the heart of a black hole's singularity, our understanding of physics shatters into irreconcilable fragments. Einstein's relativity paints a picture of space and time warped beyond recognition, a place where gravity curves infinity itself. Yet quantum mechanics insists the universe operates in discrete packets, where even emptiness seethes with virtual particles. These two pillars of modern physics, each tested and proven in their own domains, become mortal enemies at the singularity's edge. Relativity demands a smooth, continuous fabric of spacetime, while quantum theory thrives on chaos and uncertainty. The result, a mathematical battleground where equations explode into nonsense, leaving us staring into an abyss of contradictions. This clash isn't just academic, it's a crisis at the core of our cosmic knowledge. Imagine trying to describe a rainbow using only the vocabulary of sound, or explaining a symphony with nothing but colors. That's the scale of disconnect between these frameworks when pushed to their limits. Near a singularity, quantum fluctuations should, in theory, warp spacetime so violently that relativity's orderly equations collapse. Yet relativity insists spacetime must remain smooth, even as quantum effects twist it into a probabilistic froth. Neither theory yields, and the universe offers no easy answers. Enter the contenders, string theory and loop quantum gravity. String theory proposes that the fundamental building blocks of reality aren't particles but vibrating strings, tiny threads of energy whose oscillations dictate the laws of physics. In this view, the singularity's infinite density might be an illusion, smoothed out by strings too small to probe. Loop quantum gravity takes a different approach, suggesting spacetime itself is woven from discrete, interlocking loops, a pixelated reality where the singularity's infinity is simply a missing piece in the cosmic quilt. Both theories aim to reconcile the irreconcilable, but neither has yet delivered a smoking gun. The stakes couldn't be higher. Without a theory of quantum gravity, black holes remain cosmic riddles wrapped in event horizons. Their singularities might hide gateways to other universes, or they might be dead ends where information vanishes forever, a violation of quantum mechanics' sacred law that nothing is ever truly lost. Some physicists speculate that resolving this puzzle could reveal hidden layers of reality, like discovering that the flat Earth we once knew is actually a spinning globe. Others fear the truth might be far stranger, upending not just our equations but our very notion of existence. For now, the singularity remains the ultimate blind spot in our cosmic vision, a place where the universe laughs at our attempts to define it. But that's the thrill of the hunt. Every failed experiment, every mathematical inconsistency is a clue waiting to be deciphered. Whether the answer lies in vibrating strings, woven space-time, or something beyond our current imagination, one thing is certain: the day we crack quantum gravity won't just solve a puzzle. It'll rewrite the story of reality itself. Light doesn't just bend near a black hole, it fights for its life. Picture a beam of light desperately trying to escape the event horizon, clawing against gravity's grip like a climber scaling an endless wall. But with every bit of energy expended, the light weakens, its wavelength stretching longer and redder as it struggles. This is gravitational redshift, the moment light becomes a cosmic marathon runner, exhausted by the sheer effort of fleeing a black hole's pull. And here's the haunting part: the more stretched the light, the more time itself has slowed in its frame of reference. Redshift isn't just a color change, it's a ticking clock, revealing time's brutal deceleration under gravity's boot. Think of redshift like an echo in a cavern. Shout into a deep well, and your voice returns distorted, lower in pitch as the sound waves lose energy traveling back to you. Light near a black hole does the same. As it climbs out of gravity's well, each photon pays a tax in energy, stretching its wavelength toward the red end of the spectrum. The deeper the well, the more extreme the shift, until at the event horizon, light is stretched so thin it effectively disappears, redshifted to infinity. It's as if the black hole is smearing the light's final cry across time, turning it into a whisper that never quite reaches us. Now pair this with time dilation. Just as redshift shows light struggling against gravity, time dilation reveals how gravity throttles time's flow. The same force that stretches light also stretches seconds, slowing them to geological timescales. A clock near the horizon wouldn't just tick slower, it would glow redder, its light signals dragged out like taffy. This isn't coincidence, it's two sides of the same relativistic coin. Redshift is time dilation written in light, a visible fingerprint of gravity's warping power. Consider a star orbiting a black hole. As it swings close, its light redshifts dramatically, signaling time's slowdown in that extreme gravity. But from the star's perspective, time flows normally. It's the universe outside that seems to speed up, like watching the world fast forward from a prison of gravity. This asymmetry is relativity in action, no privileged frame of reference, just observers disagreeing on time's pace based on their gravitational address. The implications are staggering. When we detect light from objects near black holes, we're not just seeing distance, we're seeing time. A highly redshifted quasar isn't just far away. Its light carries the scars of a brutal gravitational journey, a testament to spacetime's flexibility. And if we could watch an object fall into a black hole, its light wouldn't just fade, it would freeze at the horizon, redshifting into oblivion as time for it grinds to a halt. The universe, it seems, has a cruel habit of erasing its victims twice, once in space and once in time. So next time you hear about redshift, remember, it's not just a color. It's gravity's ledger, a ledger written in light, where every stretched wavelength tells the story of time's surrender. A stationary black hole bends time like a lead weight on a trampoline, but give it spin, and the fabric of spacetime starts to swirl like water circling a drain. Rotating black holes, described by the Kerr metric, don't just warp time, they twist it, dragging everything nearby into a cosmic whirlpool where the rules of physics get dizzy. At the heart of this chaos lies the ergosphere, a squashed sphere of distorted spacetime outside the event horizon where not even light can resist being pulled along for the ride. Here, time doesn't just slow down, it spirals, caught in a gravitational vortex that makes a static black hole's effects look tame by comparison. Frame dragging is the star of this show. Imagine stirring honey with a spoon. The liquid closest to the spoon moves fastest, dragged by its motion. A spinning black hole does the same to spacetime itself, tugging the surrounding universe into rotation like an invisible hand turning a cosmic dial. The closer you get to the ergosphere, the more you'd find yourself orbiting against your will, your trajectory bent by the black hole's rotation, even if you're firing thrusters in the opposite direction. It's not just gravity pulling you in now, it's spacetime itself rolling like a treadmill beneath your feet. This spinning dance floor has bizarre consequences for time. Near a static black hole, time dilation depends solely on gravity's strength. But in the ergosphere of a spinning monster, time stretches unevenly faster in the direction of rotation, slower against it. An astronaut skimming the edge could exploit this to gain energy, effectively stealing a fraction of the black hole's spin. It's like surfing a wave where the water itself is made of stretched seconds, riding the twist of space-time to speeds otherwise impossible. The wildest part, the ergosphere isn't just a zone of distortion, it's a gateway to theoretical energy extraction. The Penrose process suggests that objects entering the ergosphere could split in two, with one fragment falling in while the other gets flung outward with more energy than it arrived with. Where does the bonus come from? The black hole's own rotation, its angular momentum cannibalized to fuel the escape. It's cosmic alchemy, turning gravity's grip into a slingshot, and proof that a spinning black hole doesn't just bend time. It weaponizes it, yet for all their ferocity, black holes might be the universe's most efficient time machines. Their spin could stabilize wormholes, creating shortcuts through space-time where time dilation becomes a navigational tool rather than a death sentence. Of course, the tidal forces would still shred you, but mathematically, the possibility teases a tantalizing what-if. What if we could harness frame dragging, not just to stretch moments, but to fold them? The equations allow it. Nature, ever the skeptic, might disagree, but that's the allure of these spinning beasts. They're not just dead stars. They're cosmic lathes, carving space-time into shapes we're only beginning to dream of. Science fiction loves to play with time dilation, sometimes with razor-sharp accuracy, other times with the subtlety of a sledgehammer. Take Doctor Who, where the TARDIS occasionally brushes against black holes, warping time in ways that feel more poetic than scientific. The show gets credit for capturing time's fluidity, but it often trades realism for drama, like when the Doctor outruns a time-slowing effect with sheer willpower. Contrast that with Interstellar's gut-punch precision, where every second on Miller's planet costs years elsewhere. Nolan's team worked with physicists to ensure the math held up, making the emotional weight of Cooper watching his children age from a screen feel terrifyingly plausible. Then there's Event Horizon, where a black hole-adjacent spaceship becomes a haunted house of time loops and hallucinations. It's a nightmare factory, not a physics lecture, but buried in the horror is a kernel of truth. Extreme gravity would distort perception, stretching moments into madness. The film just cranks it to 11, swapping Einstein for jump scares. And let's not forget Star Trek, where slingshotting around a star to time travel is treated like a road trip detour. The franchise handwaves the gravity equals time warp logic, but at least it acknowledges relativity exists, unlike The Flash, where speedsters outrun time dilation like it's optional. The best sci-fi uses time dilation as a narrative scalpel, not a blunt tool. The Forever War by Joe Haldeman nails it. Soldiers fighting interstellar wars return to an Earth centuries older, their loved ones dust while they're still young. It's a haunting metaphor for veterans' alienation, rooted in real physics. Meanwhile, Avengers, in-game plays fast and loose quantum realm time jumps are more plot device than science, but hey, it's got a talking raccoon. The takeaway: when Hollywood respects the science, time dilation becomes more than a gimmick. It's a lens to explore loss, isolation, and the fragile ticking of human lives against the cosmos' indifferent clock. For every arrival, where time's nonlinear flow is central to the story's emotional core, there's a primer, a low-budget gem so obsessed with accuracy it leaves audiences scrambling for whiteboards. Sci-fi doesn't need to be a textbook, but the best stories recognize that time dilation isn't just a cool effect. It's a force that bends more than light. It warps identity, memory, and the very bonds that hold us together. The next time you see a character leap through time near a black hole, ask yourself, is this spectacle or is it storytelling with the universe's own rules? The difference is what sticks with you long after the credits roll. Sagittarius A, the supermassive black hole at the center of our galaxy, isn't just a silent predator. It's a cosmic timekeeper, warping the orbits of nearby stars so severely that astronomers can watch time itself stretch in real data. Take the star S2, for example. This fiery giant whips around Sagittarius in a 16-year orbit, reaching speeds over 15 million miles per hour as it skims just 17 light hours from the event horizon. At that distance, relativity predicts its clock should tick noticeably slower than stars farther out. And guess what? Telescopes spotted exactly that. By analyzing S2's light over decades, scientists detected its light redshifting as it neared the black hole, proof of time dilation written in starlight. The graphs tell the story best. Plot S2's light curve over time, and you'll see its wavelength stretch like taffy during close approaches, then snap back as it swings away. That redshift isn't just Doppler effect from motion. It's gravity stealing energy from the photons, forcing them to climb out of a space-time well so deep that each one arrives at our telescopes older, redder, and weary from the journey. The data matches Einstein's predictions to within 1%, a triumph of theory meeting observation. But S2 isn't alone. The star S62 endures even wilder extremes with an orbit so tight it completes a full loop in under 10 years. During its closest pass, time for S62 slows by a staggering 30 minutes compared to Earth's clocks. That might not sound like much until you realize we're detecting this shift from 26,000 light-years away. The Very Large Telescope in Chile caught this star's light stretching like a rubber band, its spectral lines creeping toward the red end of the spectrum precisely as relativity foretold. It's like watching a cosmic speedometer where gravity's grip literally drags the needle toward slow. What's truly wild is how these observations double as black hole scales. By tracking time dilation in multiple stars, astronomers can weigh Sagittarius with freakish precision 4 million suns worth of mass, all measured by the way it bends starlight and time. The star's trajectories become calculator keys, their redshifted screams telling us not just that time warps, but how much. And every new observation tightens the noose around alternative theories, leaving Einstein grinning from beyond the grave. The latest breakthrough, Gravity, an instrument combining 4 telescopes into one superscope, now tracks these stars in real time, catching their light flicker and dim as they dance past the black hole. Its data reveals even subtler effects, like how Sagittarius A's spin a whopping 90% of light speed, drags spacetime along with it, twisting orbits like a spoon in honey. Future telescopes, like the Extremely Large Telescope, will push this even further, watching stars so close to the event horizon that their light loops the black hole multiple times before escaping. Imagine seeing the same photon arrive twice, first from its direct path, then from its victory lap around the singularity. That's not sci-fi. It's the next decade's astronomy. So next time you gaze at the Milky Way's hazy core, remember, hidden in that glow are stars living life in slow motion, their clocks throttled by gravity's invisible hand. And with every flicker they send us, they're whispering the same truth: time isn't just passing out there, it's bending. Time dilation near black holes doesn't just bend the universe's rules, it shatters our most basic assumptions about reality. If time slows to a crawl near a black hole while racing by elsewhere, what does that mean for something as simple as the word now? On Earth, we take for granted that the present moment is universal, that when you say right now, someone on the other side of the planet shares that same instant. But black holes laugh at that idea. For two people separated by extreme gravity now becomes meaningless. One could be sipping coffee while the other's lifetime has already come and gone, all because time itself is stretched thin between them. This isn't just a quirk of physics, it's a philosophical earthquake. If now isn't absolute, then free will, destiny, and even the nature of existence come into question. Imagine a civilization orbiting a black hole, their clocks slowed to a near stop. To them, centuries of war, art, and discovery might unfold in what feels like weeks. Meanwhile, distant galaxies evolve at lightning speed from their perspective. Who's to say which timeline is real? Relativity suggests there's no privileged frame of reference, no cosmic judge to declare one moment more valid than another. The universe doesn't care if your now is someone else's past or future. Black holes amplify this chaos by turning time into a funhouse mirror. Near the event horizon, time doesn't just slow, it fractures. An observer watching from safety would see a falling astronaut frozen in place, their last moments stretched across eternity. But to the astronaut, time moves normally, their fate arriving in what feels like seconds. So who's right, both and neither? Reality becomes a matter of perspective, where even something as fundamental as the passage of time loses its anchor. This forces us to confront an unsettling truth. Our perception of time is a fragile illusion, cobbled together by the weak gravity and slow speeds of our everyday lives. We're like fish who have never left a pond, unaware that the water itself distorts the sky above. Black holes rip away that comfort, revealing time as a fluid, malleable thing, not a river flowing in one direction, but a stormy sea where currents twist and collide. The implications ripple into everything from ethics to identity. If time is relative, can we truly say someone's actions are past or future? Could a decision made near a black hole echo backward in time for someone far away? These aren't just thought experiments, they're cracks in the foundation of how we understand cause and effect. The universe, it seems, operates on a logic far stranger than our own, where the very fabric of reality is negotiable. And that's the real terror or thrill of black holes. They don't just warp space-time, they warp meaning. In their shadow, the questions outnumber the answers, leaving us to wonder, if time is this fluid, what else about reality might be up for grabs? Surviving near a black hole isn't just a sci-fi fantasy, it's a physics puzzle where every second comes with a brutal exchange rate. Picture a starship, engines screaming at full thrust, holding position just outside the event horizon of a supermassive black hole. The crew inside might experience time normally sipping coffee, running diagnostics, completely unaware that back on Earth, civilizations are rising and falling in what feels like the blink of an eye. This isn't just dramatic storytelling, it's the raw math of relativity in action. For every minute the crew spends hovering near the abyss, decades or even centuries could pass for those left behind. The numbers are staggering. At a distance where time dilation stretches 1 hour into 7 years, like Interstellar's Miller's planet, a short research mission could strand the crew returning to an unrecognizable home. But how? Let's break it down. Time dilation near a black hole follows Einstein's equations precisely. The stronger the gravitational field, the slower time ticks relative to areas with weaker gravity. For a ship skimming the edge of a black hole's influence, the difference isn't linear, it's exponential. Even a modest black hole with a time dilation factor of 1 to 10 would mean a 5-year mission for the crew equals 50 years on Earth. Push closer and the ratios explode. Near the event horizon of a supermassive black hole, 1 Earth year could translate to mere minutes on the ship. The crew could watch the sun's lifespan flash before them in real time, stars dying and galaxies colliding outside their windows like a time lapse of cosmic doom. The real horror: communication breakdown. Radio signals sent home would redshift into oblivion, stretched so thin they'd arrive as faint whispers centuries later. The crew's live messages would reach Earth as ancient relics, their senders long gone in the eyes of history. Even worse, any reply from Earth would blue shift into lethal gamma rays by the time they reached the ship, frying the crew with energy meant as a friendly hello. It's a paradox of isolation, being physically close to the universe yet cut off from it by the very laws of time. Yet here's the twist: from the crew's perspective, nothing feels amiss. Their clocks tick normally, their hearts beat at a steady rhythm. Only when they try to leave would the truth crash down. Disengaging from the black hole's grip would require unimaginable energy, like climbing out of a gravitational well with infinite walls. And even if they escaped, the universe they'd return to would be alien, a future where their loved ones are dust, their nations forgotten, their very existence a footnote in history. This is the cruel irony of black hole survival. You don't die from the spaghettification or the radiation first. You die from time itself, from watching the universe move on without you, stranded in a pocket of slowed seconds while eternity rushes by. It's the ultimate prison with bars made of distorted space-time. And that's the real lesson. Near a black hole, survival isn't about withstanding gravity. It's about confronting the fact that time, not space, is the most unforgiving frontier of all. What if the ultimate time capsule wasn't buried underground, but parked just outside a black hole's event horizon? Imagine a data vault where civilizations could store their knowledge not for centuries, but for cosmic epochs, letting relativity's time stretching effects do the heavy lifting. A black hole's gravitational grip could turn mere hours into geological eras for the outside universe, creating the perfect archive for cultures wanting to outlast the stars themselves. Think about how we preserve information today: stone tablets, hard drives, DNA storage, all vulnerable to decay over millennia. Now picture a crystalline memory bank in stable orbit around a black hole, its atomic structure reinforced against tidal forces while time dilation handles the rest. Upload your entire species' history, art, and science into this orbital vault, and by the time 1,000,000 years pass on distant Earth, only days or weeks might elapse for the data itself. It's like hitting pause on history's remote while the universe presses play at full speed. The engineering challenges are monstrous, of course. Any storage medium would need to withstand the black hole's radiation bath and gravitational stresses without being shredded into quantum confetti. Perhaps a swarm of self-repairing nanomachines could maintain the archive, or maybe the data would be encoded in the quantum states of particles orbiting just outside the danger zone. Either way, the payoff is staggering. A library where knowledge could survive not just the collapse of civilizations, but the death of galaxies. Here's where it gets even wilder. Advanced beings might not stop at passive storage. They could use black holes as literal time mail servers. Send a probe carrying messages into a high dilation orbit, and the recipients could retrieve it millennia later without aging a day. Want to communicate with the far future? Drop your data near the event horizon and let the universe's own gravity handle the delay. The black hole becomes a cosmic post office where overnight delivery takes eons from the sender's perspective but arrives instantly for the recipient. The ultimate twist: these time capsules could double as emergency bunkers. A society on the brink of collapse might stash its greatest minds in suspended animation near a black hole, slowing their subjective time until the universe outside becomes habitable again. They'd emerge into a new cosmic era, their original world long gone but their knowledge intact, like waking from a nap to find the ice age over and cities gleaming where glaciers once stood. Of course, there's a dark edge to this dream. Any civilization mastering black hole storage would wield power over time itself, deciding which truths survive and which vanish into the abyss. Would they curate knowledge for future species or hoard it as galactic leverage? Could these archives become traps, luring curious cultures too close to the event horizon's deadly embrace? The ethics twist as strangely as space-time itself when you're playing with time dilation as a tool. Yet the possibility remains tantalizing. Black holes may be nature's perfect time locks, offering a way to cheat entropy's erasure. In a cosmos where stars burn out and galaxies fade, these gravitational marvels could serve as the ultimate keepsakes, preserving whispers of lost civilizations in the stretching of seconds, long after their creators have turned to dust. The universe has an expiration date. Stars will burn out, galaxies will fade, and space itself will stretch into a cold, dark expanse. Yet amidst this cosmic decay, black holes will endure, not just as relics of a brighter past, but as the last keepers of time in a dying universe. These gravitational titans, having feasted on stars and galaxies for eons, will outlive every other structure in existence. And as the cosmos grows colder and emptier, their event horizons might become the only remaining markers of time's passage in an otherwise timeless void. Picture the distant future, trillions of years from now. The last stars have flickered out, their ashes scattered across an ever-expanding darkness. Planets have crumbled to dust, and even the protons that once built atoms have decayed into radiation. Only black holes remain, their immense gravity defying the universe's slow unraveling. In this desolate era, time won't just slow. It will lose all meaning without events to measure it. No sunrises, no orbits, no ticking clocks, except perhaps for the Hawking radiation leaking from these lone survivors. Here's the twist: black holes themselves decay. Through that same quantum quirk that makes them evaporate, they'll slowly leak energy over incomprehensible timescales. For a stellar mass black hole, the process might take longer than the current age of the universe. A supermassive one could linger for gugolls of years, but eventually, even they'll vanish in a final burst of radiation. Until then, their evaporation acts like a cosmic hourglass, each particle escaping a tick in the darkness, a faint echo of time's persistence. But could something, or someone, use them as clocks? Imagine a civilization clinging to existence in this frigid far future, their ancestors having long mastered black hole engineering. With no stars left to orbit, they might turn to these gravitational behemoths as their timekeepers. By measuring the rate of Hawking radiation, they could deduce a black hole's mass and thus its remaining lifespan. Each shrinking hole becomes a countdown timer, its evaporation rate ticking slower as its mass dwindles. It's a grim calendar where the passage of millennia is marked not by rotations or revolutions, but by the fading glow of space-time itself. The darkest irony: even this last measure of time is doomed. As black holes evaporate, space grows colder, stretching the intervals between their particle emissions. The ticks grow farther apart, the cosmic clock winding down. In the end, the last black hole's final burst will be more than an ending, it'll be the universe's last discernible event. After that, time won't just be irrelevant, it'll be impossible to define. No change, no entropy, no before or after, just an infinite, featureless now. Yet in their solitude, black holes offer a strange comfort. They remind us that even in the void, time leaves fingerprints. Whether by the stretch of seconds near their horizons or the slow leak of their demise, these gravitational titans will be the last things in existence that still, in some way, tick. And when even they're gone, time, that fleeting, fragile construct, will dissolve like smoke in the wind, leaving only the silent, eternal dark. Time dilation near a black hole might stretch seconds into centuries, but even gravity's grip has its limits. No matter how close you get, you can't freeze time completely. The universe enforces a cosmic speed bump, Planck time. This is the smallest meaningful unit of time, roughly 10 to the power of minus 43 seconds. Shorter intervals simply don't exist in any physical sense. At this scale, space-time itself stops behaving like a smooth fabric and dissolves into a seething quantum foam, a turbulent froth where gravity and uncertainty wrestle for dominance. No matter how much a black hole warps time, it can't slice reality finer than this. Think of it like trying to slow down a movie frame by frame. You can pause it, examine individual moments, but eventually you hit the pixel limit of the film itself. Time dilation near a black hole is similar. You might stretch a second into a millennium, but you can't fracture it past Planck time without breaking physics itself. Even at the event horizon, where time appears frozen to outside observers, the universe's quantum bedrock ensures that something still happens. The doomed astronaut falling in doesn't truly freeze. From their perspective, they cross the horizon in finite time. The illusion of stasis is just a side effect of light's desperate, infinite struggle to escape. This quantum granularity throws a wrench into sci-fi fantasies of eternal time locks or perfect stasis chambers. Want to pause a civilization's collapse by parking it near a black hole? Fine, but Planck time means their clocks never fully stop. Quantum fluctuations will still ripple through their reality, ensuring change happens even if it's imperceptibly slow. And here's the kicker: at these extremes, time and space start to blur. The very idea of before and after gets messy when gravity twists causality into knots. The takeaway: black holes bend time like a funhouse mirror, but they don't shatter it. The universe has guardrails written in quantum foam and Planck scales, ensuring time never truly stops, just stretches beyond recognition. So while you might outlast civilizations by skimming a black hole's edge, eternity remains stubbornly out of reach. The cosmos refuses to let anything, even gravity's might, freeze its clock entirely. If you dropped a clock into a black hole, here's exactly what would unfold: a spectacle where time doesn't just slow, but fractures into an eerie performance. At first, the clock would plunge toward the event horizon, ticking normally from its own perspective. But to you, watching from a safe distance, its descent would quickly turn surreal. As gravity's grip tightens, the clock's ticks would stretch, first milliseconds apart, then seconds, then minutes. The hands, once crisp and precise, would crawl like they're stuck in molasses. Meanwhile, the light from the clock's face would redshift, its glow shifting from white to deep crimson as photons fight against the black hole's pull. Then comes the freeze. The closer the clock gets to the event horizon, the more time for it appears to stop from your viewpoint. The final tick, the one where the clock crosses the point of no return, would never actually arrive. Instead, the clock's image would smear across the void, its last visible moment stretched into an infinite fade. The light it emits just before crossing would take longer and longer to reach you, like a message trapped in amber. Eventually, the clock's glow would dim to nothing, redshifted beyond detection, leaving only a ghostly silhouette imprinted on the black hole's edge. But here's the twist: the clock itself experiences none of this drama. For it, time flows normally, right up until tidal forces rip it apart. Its final moments are business as usual, even as your perspective paints them as frozen forever. This disconnect isn't a glitch, it's the universe enforcing relativity's ruthless logic. Time isn't a universal metronome, it's a local experience warped by gravity's whim. Now amplify this with a modern twist. Imagine the clock is a smartphone broadcasting live video. At first, the feed streams smoothly, but as the phone nears the horizon, the video buffers, each frame delayed longer than the last. The audio drops in pitch, voices slowing to demonic growls. Then the stream stutters to a halt, the last pixelated frame lingering on your screen indefinitely. The phone's fate, oblivion, but to you it's eternally teetering on the edge, a digital ghost trapped between existence and erasure. This isn't just hypothetical. Astronomers observe similar effects, with stars being devoured by black holes, their light stretching into an endless fade, their final orbits smeared across telescopes like cosmic brushstrokes. The universe, it seems, has a flair for dramatic exits, and in that drama lies a profound lesson. Near a black hole, even time itself can't escape being rewritten. Gazing into the swirling abyss of a black hole isn't just a spectacle, it's a confrontation with the universe's most mind-bending secrets. We've journeyed through the physics-defying realm where gravity doesn't just pull matter, it stretches time like taffy, turning minutes into millennia and seconds into centuries. From Einstein's equations predicting time's slowdown near these cosmic monsters to the eerie reality of stars like S2 orbiting Sagittarius A, their light redshifting under gravity's vice grip, every observation confirms it. Black holes are nature's ultimate time machines. We've seen how spaghettification shreds objects atom by atom, while time dilation smears their final moments into eternity for distant observers. We've wrestled with the paradox of Hawking radiation, where black holes slowly leak energy, and the terrifying beauty of frame dragging around spinning singularities, where space-time itself becomes a swirling vortex. But here's the real kicker: black holes aren't just destroying time, they're revealing its true nature. They show us that time isn't a fixed river but a malleable fabric warped by gravity's touch. Whether it's the heart-wrenching time skips in Interstellar, the quantum chaos at the singularity, or the hypothetical white holes spitting out alternate realities, one thing's clear: our universe is far stranger than we ever imagined. And that's the thrill. Every black hole is a riddle wrapped in an event horizon, daring us to look deeper. So now it's your turn. What's your wildest vision of time dilation? A civilization surviving near a black hole's edge, watching galaxies rise and fall like passing storms, a message sent into the future by skimming the event horizon. Or something even crazier? Drop your ideas in the comments. We're all just cosmic storytellers here, trying to make sense of the universe's greatest hits. And if you're craving more mind-bending journeys through space, time, and beyond, hit that subscribe button. The cosmos has endless secrets left to unravel, and we're just getting started. Until next time, keep looking up, and remember, in a universe where time bends, even the impossible might just be waiting for the right equation.